This is the asynchronous machine model in EMTP, where like most options are selected. So here you have run, rotor, and so on, which is selected in this one. This model is based on the part transformation. So just a quick reminder what the part transformation is. It is used to go from the ABC domain to the DQ0 domain, which is common to simulate rotating machine. So that's where all the equations will be solved on the DQ0 domain. So it's just a mathematical equation using certain eigenvalue. So it's a specific transformation which is called the part transformation. The equation of the asynchronous machine looks like that in the DQ0 domain. It depends, of course, if you are a single cage, double cage, then you have extra lines. The flux equations are written here. So the flux intervene at this part on the previous equation. All right, so let's see the asynchronous machine in EMTP. So let me maybe switch to the software. Okay, so it looks like that. If you open the mask, so you double click to open the mask, you have to enter the rated power, the power factor. So like always, you have here the tooltip when you point on a description. Also, you have the help available if you need something. Then here you have the stator line-to-line voltage, rated voltage, the frequency, the number of poles, the type of connections. In the current version of EMTP, the version 4.1, it is not really recommended to use the load flow solution to initialize the asynchronous machine like it is done with the synchronous machine. The reason is because when you will use the load flow bus, you will have to specify a P and Q. But for an asynchronous machine, you cannot control P and Q independently. Those are linked. So very often you will not be able to achieve a perfect initialization with a load flow bus. So that's why most of the time, if you want to have a synchronous machine initialized and up and running at the first time step, you will have to here use the reference frame. You can use the fixed stator and initialization method steady state. And then here, enter the steady state slip. What you can do, the recommendation is to enter here the rated slip, and so then run a simulation. And if you see that you're already off and that the actual simulation slip is not the one, is not the rated one, well, you can run one simulation, look at what is the final value of the steady state slip, and then modify it from here. To visualize the steady state slip, you will go to the Observe and Scope tab here and simply select here mechanical slip. Okay. Then in the machine, you will be able to apply an external torque. Let's say, for example, your machine is a motor or a pump, and it's moving, it's moving something mechanical. Then here you have in order for this part not to cause a problem for initialization, you can decide here to start applying this torque at a certain point. Here, for example, 0.01 second. Before that, the speed remains constant. Okay, so that's how you will initialize your synchronous machine. You also have the options to simulate saturation for the synchronous machine. You may put that on the D-axis only. So in this case, you will use the open circuit test, put the D-axis current, D-axis voltage, and that's how you will have your saturation. If you have more data, you can put an independent saturation on the two axes. Moving to electrical data, you have several options here the way you input data. You can select basic options. In this case, you will directly enter the circuit parameters. You may find those from another software if you are using another software, or if you have your own calculator. Or the other option is to use here enable nameplate input calculator. This one is nice because you will input the nameplate input, like the full load efficiency, the full load power factor, full load slip, starting current, starting torque, design ratio. Then you will press the calculate circuit parameters, okay, and everything you need is here. And by clicking on this link, you will actually apply them. Here they were applied already, but see if I modify this value and if I click there again, you see it modifies things. You may also add an extra saturation here, so the saturation of the leakage inductance. Often this input you can it may not be provided. However, when you can find it by doing trials and error, basically trying to re-simulate a startup case and adjusting this value to get a better fit on the result. Of course, all that is a fitting process, so you may have little errors in the fitting process, not an absolute precision, so then you can use this value for that. Then, similarly to the synchronous machine, you have a mechanical data tab, which is based on multi-mass model. So you have here the option to enter the moment of inertia, either in second, if this box is checked, or the actual inertia, if you don't check this box. Then you have, let me zoom a little bit, then you have the speed deviation, the mutual damping. Here we don't have mutual damping because we have only one mass, and etc. By the way, I just zoomed here. To zoom, you press Control and you scroll in and out if you want a better better visualization. If you want to model the mechanical parts of the external load of the machine, for example, for a pump, if you want to model the pumping circuit and basically how you model that, typically it's you have for certain speed, this system will provide a mechanical torque, so we'll apply a mechanical torque, a resistance torque to the shaft of the machine. Well, you can, it's what is done here. In this case, you will have to go here to angular velocity and make this parameter available. So you simply click here, and here I apologize, but it opens on another screen, but you can check on your side. When you click here, you will have three options: observe, scope, and observe plus scope. As long as observe is selected, you will have this output pin here and the data omega provided in here. Okay, so the omega is in radian per second. You have the option here to also lock the rotor if you have a negative speed. So that's an option. All right, so then we go to the control tab. So you may control either the speed or the mechanical torque. Here, in the case of a pump, we will control the mechanical torque. So again, the way we will model the full process here, the pump circuit, we will have the measurement of the speed available here as an output of the machine. And then here we have the model of our process. It's basically just an equation. It can be a polynomial where the x in the polynomial is the speed and y is the torque. So the result of the polynomial is the torque of the process. Or it can simply be a curve with some data. And you may model that by replacing this device by a table function. Okay, so let me demonstrate that quickly in case you don't know. If you click here on control, you have the table function that you may use. And here you may enter the points, I don't know how many, but you can enter the points speed, torque, and then connect that here. Whereas in this case, as you see, we are using a polynomial that is written here. And so that's the equation torque speed, which is written back, and that will provide a resistive torque to my machine. All right. So then, so that's it. In my case here, the torque will be provided in per unit. So I have to check this box. Then I go to observes, and in my case, observe and scopes. I don't have any observe. The only one I needed here was the speed, but the speed is selected is the mechanical data. But you may also select some scopes. Here we have the electrodynamic torque and the mechanical slip in per unit, as you can see checked here. For precision, I don't really recommend you to play with those parameters, except if you really know very well the model. Typically, if you have a problem one day simulating many machines, you may get in touch with us and we may start playing with those, but it's not so often. Okay, so you have the documentation, of course, like any model. The documentation here is very well done. You have all equations written in here, everything you need, really, the circuits. So I really recommend you to get into that if you want to know the model better. Okay, so let's quickly take a look at that. Here you notice that we have a connection which is armature winding connection Y. Okay, you have the option to ground it automatically, but here we want to put a grounding resistance. As you can see in this case, the resistance is very high, so it's basically ungrounded. Make sure to use a neutral device here to connect the three phases together, but leave them ungrounded. One common mistake will be here to basically connect the neutral to a big resistance here, but in this case, there is no neutral. Basically, the three phases are grounding through a resistance, but the three phases are not connected together. So now the machine model will not work anymore. Okay, what you have to do is go grab a neutral here. Okay, now you see you can find it in machine or in pseudo devices. And then connect in a very high resistance, 1 mega ohm if you want it ungrounded, and if you want it grounded with another resistance, just change the value. But so this part here is single phase. It shouldn't be three phase. Okay, then as explained, I have here my bundle. Okay, to do an outbreak, to select this signal. The way to do it, it's fairly easy. You simply right click, you go to breakout, and you select what you want. If you have more signals, you can delete them if you don't want them in your breakout. Okay, let me actually redo that. So you right click, you go to breakouts, you have omega, you just click on OK. Using arrows, you can change that and connect it here. Okay, so now it's connected again. The speed here is in radian per second. If you enter a polynomial in per unit, you have to put that in per unit as well. So the base is like that. It will be 2 pi frec. So frec is the 60 hertz in this case, and number of pole pairs. Okay, here we enter the number of pole. The pole pairs is 3. Okay, so here this number is the inverse of that. Like always, you guys probably know that already, but you can write that here. 1 divided by 2 multiplied by pi multiplied by 60. Multiplied by 60 and divided by 3. And we find here the same number. The number was rounded just so it's not so big. It does not really matter. But all right, so let's do this simulation. Here we energize this. This machine. So let's try that out. Oops, I have an error. Sorry about that. Oh yes, it's because I changed here to I changed the initialization method. So let me remove that and start over again. Okay, then we visualize the result with scope view. Oh, those were signals previously selected. Okay, so when you have this machine here with scopes, one thing you will have is a signal type machine. From here you can see what was selected in the scope tab of the machine. So we had the slip, we had the speed, and maybe let's take a look at the current here. I think it's selected in switch current. Let's focus on phase A only. All right, so you see when we energize the machine right at the beginning. So we have, I don't know, maybe we can zoom a little bit. Oh, it's actually right at the beginning. Let me do this simulation again, but switch the machine slightly after, just after a cycle, so we can see. Okay, so you see initially nothing, then we energize the machine. So we have the starting current here. And when the machine reach, at this point, you can see the slip and the speed. At this point here, we reach the steady state, so the current goes down to a regular value. So this is here the starting process. Many interesting things you could do with EMTP, for example, energize the machine with an open phase. If you have an open phase problem, you could put here some overcurrent relays from our relay library to make sure nothing trips. You can evaluate the voltage sag when you energize this machine on the grid side and make sure the power quality is good enough and you don't have a voltage drop. So we see here, if I select this, any curve, and I go to take the double cursor just to evaluate how long it took. We see that it took about 15 seconds to start. Okay. Now, if I want to see, do we have the current? Let's visualize actually the current in per unit. Doing machine current. Okay, so what we can see is that the peak current here is 7.67 per unit. If we look at the inputs that we had here in electrical data, the starting current was 6.8. So it's actually pretty good. And this one actually, it's not where I should check because there is the DC component, but it's more the next one. See, it's 6.9. 6.9 is very close to what we wanted. Okay, you can check out the influence of this parameter. For example, let me remove it and save the result, the 3 results that we have here, and run this again. Okay, so you see how it affects the starting time. Now I start later. So you may play with this parameter if you know the starting time of your machine and the initial, and you want to adjust it to really match, you can use this parameter. All right, now let's, one last thing, let's say I want to have this machine already there in steady state. So I now close this switch, so the machine is connected to the grid initially. Then the only thing I have to change is the initialization method, go to steady state. I'm going to keep here synchronous. And like I said, I'm going to use the full load slip to initialize the machine in %. All right, so let me start the simulation. I can remove what we have memorized. Okay, so now you see that we have a current. So it's actually not perfect, as you see. We have a first, we have a transient, and we see that the final slip is 0.014. So let's change that right here and put here 1.4 and see if now it gets better. Again, we see that indeed it's much better. here the axis changed, but if you see now the current barely changed. And I can actually make that even better if you do this process several times. Here I just have to add 5, 8 after. In incoming version, we'll probably add a specific load flow bus just for synchronous machines. It's not here in this version, so that's why you have to do it that way. But you see that eventually you can achieve perfect initialization and then start doing many more studies. If you have one last point, if you have a round rotor machine, like it's the case, for example, in DFIG wind turbine, you may select that also here in electrical data and select one rotor. So in this case, you will have here the possibility to connect whatever is on the rotor side. It's also used for variable frequency drive, actually. All right, thanks for watching this video. I hope you enjoyed. Have a good day. Bye. Okay, just a quick addition to the video to explain in detail again how to connect the load model of the asynchronous machine. So let's say if it's a pump, this will be the pumping system. If it's a load, it will be, I don't know how the load is moving. So what we have here, so we have a polynomial, which is typically provided, which will depend on the viscosity of the liquid in the pump circuit, or will depend on whatever you're moving with your machine, if it's a conveyor or something like that. So here you enter the polynomial. The x of the polynomial is the speed, and the y is the torque. Instead of using such a device, you may use the table function and enter the curve here. The x will be the speed again, and y will be the torque. Both devices are found in the control library. This one is called a function of u here. Okay, so basically what we need here is the speed as an input and then control back the torque. So let's start with that. We go to the tab control and we select here mechanical torque. My function here is given in per unit. The output of this function is in per unit, so you have to select this box and click on OK. So right now you see I have a pin which just added. And so then it's fairly simple. I right click on that and click on breakout. I see I have TM like mechanical torque. I click on OK. And then I just connect those two together. Okay, so now they are connected. For the speed, it's almost the same thing. I go there. I go to mechanical tab. I have here something called angular velocity. You click here. You cannot see it because it's on the other screen, but you select something called observe, and or observe plus scope, and you click on OK. In the version 4.2, the speed cannot be put in per unit, so you have to use the value in radian per second. Okay, so same thing, you click on the bundle here, you go to breakout, then you click on OK. Put that on, you can change the orientation using arrows, connect here. So the only thing you have to do here is because in the curve provided, the speed is assumed to be in per unit. I have to put that in per unit. So for that, I can use a gain or a loss, which is shown here. Let's do one or the other. Let's use the loss. I will here change direction and put it here. And so in this case, this is here the base. So I double click. I go to constant and I write this equation. So I have to start with equal 2 multiplied by pi, multiplied by 60 the frequency, and the number of pole pair is 3. This machine has 6 poles, so 3 pole pairs. And I click somewhere, you will see this number, and you click on OK. And so now your machine is all set. if you start the simulation, it should run without any problem.